Well, welcome back, standard geometry students. I hope that you're learning a whole lot of geometry and having some fun doing that. Well, I really enjoyed all of the jokes, but I have to say one of my favorites was what happened to the math teacher when she was afraid of negative numbers. She would stop at nothing to get rid of them. I thought that was pretty funny. So anyway, I welcome back, and this is actually the last two sections in the book here. Next week we'll be doing a review, and then we will have a quiz, okay? And so we're kind of winding down the year already. So good luck to those of you that are in any of the AP courses and all that good thing, but we're winding down now. So today we're going to be doing 12.6 and 12.7. And then next week we'll be doing a review of everything that's on that last quiz. And then of course the quiz. And then that last 2 days will be for you to submit any makeup work and make sure we haven't made any mistakes. Okay? So this week is normal. We're still going to do the YouTube videos and everything else, but just kind of looking at that we are winding down. So you can kind of see that as we end chapter 12. Okay, let's go ahead and get started here. This is 12.6. So first of all, let's get started in your notes with a little bit of review. 12.6 is working with segments instead of angles. So it's going to be segments and their relationships in circles. But before we get started on the whiteboard with that, I kind of wanted to review a little bit because that'll help you understand where all these relationships in these circles are coming from. So remember, first of all, that last week we worked with arcs, and that's on the outside of the circle. Now we're working back with segments, just like we did way back in quarter one of geometry. Okay, the review that I wanted to look at is, remember what happened when I had this symbol. That symbol meant similar. And so I could say like the triangles would be similar by like angle, angle, or side, angle, side, or side, 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 side similarity. But if the triangles were similar, let's say they were similar by angle, angle, then you could write down the relationships. So remember that would be AB over the first two here, XY, is equal to BC over YZ, and of course we could have said AC over XZ, okay? And that's by the definition of similar triangles. So if you know the triangles are similar, you write a proportion. And then what did we learn to do with every proportion? We cross multiplied. So cross multiplying meant AB times YZ, see how we cross multiply, is equal to XY times BC. Okay, so just wanted to start off with that review. So let's go ahead and do another little review here. Remember, we already have had some segments when we worked with before in saying that if I had two tangents, so here I'd have two tangent segments. Remember what happened with our two tangent segments? If I had two tangent segments, they would always be congruent. Okay, so we already have this rule, don't want you to forget about that, that all I do if I have two tangent segments is just set those equal to each other. So in this case, this segment AB would equal my other tangent segment AC. So we did that before, and I'm literally just writing then AB as 2x plus 5 is equal to 3x minus 6. And solving that, so subtract 2x and add 6. Okay, and so that's our first review. Tangent segments are congruent, so AC and AB are the same, and part equals part. Now, what we're going to be looking at today then is our new, so remember we're working with segments now. The arcs are in degrees on the outside. We're now looking at the segments. So in these segments, they would be touching 2 points on the circle. So I really have two chords. Now, how does that go with the first thing we reviewed? Well, if I just make a segment from D to E and from G to F, do you now see I have two triangles? And what do you suppose is going to be true about the two triangles? Well, you're exactly right. They have the angle H here as vertical angles. Okay, and then what kind of an angle is angle E? That would be an inscribed angle. And remember, an inscribed angle is half its arc. So it would be half of arc DG. Now, why is that important? Because I have another inscribed angle over here that's also half of arc DG. So that you can see from what we learned last week that these two angles would have to be congruent because both angles are inscribed angles and they have the same intercepted arc. So essentially we're doing just like I started with and said, you know, all we're looking at is to say I have DHE, so I'm looking at DHE, and that would be similar to GHF, just like we did in the review by angle-angle similarity. So we're not just making up things, we're saying, hey, this is really going to be true. Now, remember, we don't have a DE or a GF because we really just kind of wrote those in, so we won't look at those. We'll just go with our second step then. DH over GH is equal to, just like we did in the review, remember we're looking now HE, our last two, over what? HF, our last two. And that would be just the same by the division, or excuse me, by the definition of similar triangles. So just like what we just reviewed, I just want to show you where these theorems are coming from today. So you're really looking at it saying, hey, they're really just similar triangles. So now what do you do once I have a proportion? You cross multiply. So DH times HF is equal to GH times HE. Okay, and of course that would be the cross product property. Now take a look at that because this is really now, I kind of put that all up there as an explanation as to why we're multiplying, because it comes from similar triangles, which means I have proportional sides, which means I have a cross product, but we're not going to show that today. We're just going to do exactly what it says here. So if it says in my green problem here, find X in my green circle, I'm looking at it and saying, oh, all I have to do is take DH. Well, look at that. DH is just 10. And multiply that by HF. So look, all we're doing is going along one chord and saying if I go along one chord, I multiply the two parts. So you don't have to show all this at all. It just kind of shows you where it came from. All I have to write is 10 times X. And of course, that's going to be equal to GH. Well, G to H is 8. Times H to E. H to E is 5. And so I come right to saying, hey, I really have a shortcut here, and that's all we're looking at today. Really, today's pretty good, easy lesson because we're just saying, hey, look, all we're doing is take one chord, multiply the two parts, and then equals the other chord, multiply the two parts. So I just get 10x is equal to 40, divide both sides by 10, and we are done. So our first part that we're learning here today then is a very important theorem, but I like to shorten it, really short and sweet, to say it's a chord-chord theorem. So that just means part times part equals part times part. Okay? So remember what we had from before isn't going to work. These are not equal to each other. Obviously, they could be one longer than the other. And I'm not saying the chords are even equal to each other. I'm just going along one chord and saying this part times this part equals, go along the other chord, this part times this part. Okay? So that's our new theorem, our chord-chord theorem. So now what you're looking at then is to say, oh, it's as simple as just looking at it and saying, as long as I'm working with segments. Now remember, we've been working with the angles before. This is segments. I just look at one chord and I say multiply the two numbers on that chord, 3 times x. Then I look at the other chord, multiply the two numbers on that chord, 2 times 6. That's all the work you need to show. You don't need to show all that stuff with the similar triangles. I just want to show you where it came from. So then I know that 3x is equal to 12, divide by 3, and my x is equal to 4. Okay, and it truly is that easy. Okay, so we get to end the year with a pretty easy stuff when we're working with segments. Now, that's not the only kind of segments though, because obviously they aren't always going to intersect on the inside with two chords, because we already had, if I had two tangents, what happened. So now let's see if we can figure out what's going to happen if I don't have two tangents, but I have maybe two secant segments. Okay, so I probably should use a different color. Let's try using red here. Okay, so we have a different color for each of our theorems. Okay, so two secant segments. Well, remember what a secant is. A secant is a line that contains a chord but intersects. So these would be secant segments. Now, we're not working with the same thing as we had from before. We're not looking at it and saying, oh, we have an arc, okay? Because we're working with segments today. And we're essentially looking at the same thing, but I'm not going to go through the similar triangles here, but we're really looking at the similar triangles by marking in my triangle here and my triangle here and saying that they would have to be similar, okay? So what we're going to end up with then is to say, oh, now that I have the vertex on the outside and it's made by a secant and another secant, or we could even have it a tangent involved with it, then all I'm going to do is to say, well, let's just multiply. So if I said I had, let's just put in numbers here, 4, 6, and 3, and x. Okay? So now remember what we're looking at. It's not going to be just the part times the part, because now I have to work with that whole triangle. So what I'm going to do on this one is when I have the vertex on the outside, I'm going to do the part outside, because that's going to be a side of the triangle. So when you put that segment in, the side of the triangle becomes the 3. So I'm going to do the part outside, and then I'm going to take that times the whole segment. Now that's where it gets a little tricky, because sometimes I might have to add, not always, but sometimes I might have to add to find that whole segment. Then I just change to the other secant segment and I do the exact same thing. So it's still working with similar triangles, but we're now going to see that we're just doing the part outside times the whole equals the part outside times the whole. Okay? So it's really that simple. Just got to remember to go on the outside and work to the inside. So here I would solve this by saying that's 4, the part outside, stay on the same secant segment and add them together. 4 plus 6 equals, and then stay on the outside, 3, and then whole thing, 3 plus x. So it's part outside times whole equals part outside times whole. So if I have 4 times 10 equals 9, and remember you might have to distribute this, plus 3x. So I end up with 40 is equal to 9 plus 3x, subtract 9, I get 31 equals 3x, divide by 3, and x equals 10 1/3. Okay? Now I like to look at it and say there's really just two, anytime I have segments, there's just two new segments. Now remember, it's not always if the vertex is outside, because we have this one where it was equal. But any other time, if the vertex is outside, all you do is the part outside times the whole equals the part outside times the whole. So let's take a look and see what happens there then. What happens when I end up, like on this one, I have the vertex outside, so I am going to be looking at part outside times whole equals part outside times whole, but now I have a tangent segment. Now notice they're not both tangent segments, so I'm not going to multiply just saying they're equal. This one is the secant. So I'm going to do it just the same way though. The part outside and the whole segment are the same thing. That's the only difference. So part outside times whole equals part outside times whole. So it's not any different. It's still vertex on the outside, part outside times whole equals part outside times whole. Okay? Just remember when it's a tangent, the part outside and the whole, it could be the same thing. So here I'm going to remember to do x times x. That would be x squared. 5 times 15. Whoa, 15 plus. Forgot my plus sign because I'm running out of room there. Because I've got to remember it's the whole thing. So it's 15 plus 5. So it's going to be 5 times 20. Oops, can't see that very well. That makes sense? So part outside times whole, part outside times whole. Okay, well then that makes it x squared is equal to 100. Take the square root of that, and x is equal to 10. Okay, so you're really just looking at part outside times whole equals part outside times whole, or part times part equals part times part. So it's a pretty easy assignment. And I really like the second part of this assignment on 12-7. It's easy also, but I kind of remember it in terms of a guy named Mike Tyson. You guys ever remember anybody about Mike or anything about Mike Tyson? Who's Mike Tyson? Well, I don't know who he is. Well, let me tell you about Mike Tyson. Mike Tyson was a boxer, and yeah, you're right. He's saying, is he the one that bit off someone's ear? But that's a whole different story. He was in jail for some reasons, and he did not have his high school degree. And so he took a GED, and he failed the GED. So what was the question that he commented on in the newspaper? You don't know? Oh, well, it was, if x squared plus y squared equals 34, what's the radius of the circle? Well, we're going to find out. So you just sit right tight and we'll see how easy this actually is. Okay? So keep in mind, we're going to look at today, if x squared plus y squared equals 34, what is the radius of the circle? This is the exact same question, you can look it up online, that Mike Tyson missed when he was doing his GED. And I never could find out whether he ever did get his high school diploma. Okay, so let's take a look at it and see how we could do this. Well, we're looking at it and saying, well, let's take a look at a circle that we know that the center is A being 2, 3. So this is 12-7, our last section in the textbook, circles in a coordinate plane. So woohoo, we're on the last section. So we have center A at 2, 3, so I've already graphed it, and the radius is 4. I want an equation of the circle. Now, is A part of the circle? No. Is the radius part of the actual circle? No. Only these points are part of the actual circle. So how many points are on this circle? You're right, an infinite number. So we really just think of any one of these points as x comma y. It doesn't matter where they are, because if I came over here, the radius would be 4, 4, 4, 4. It doesn't matter. The radius wouldn't change because it would be in the same circle. So let's just pick the one that's already here and say that's x comma y. Now, do you see what we have? 2 points, and we have the distance between the 2 points. So you're exactly right. All we're really looking at is the distance formula. What's the distance formula? The distance formula, just like we practiced for all those times for the EOC that we didn't have to do, x1 minus x2 quantity squared plus y1 minus y2 quantity squared. And that's really what we're looking at here. We're simply going to tweak it a little bit. So we already know the distance. The distance here is what? 4. So we're going to say 4 is equal to the square root of, and what are my x values? Well, one of them I don't know, so I just leave it as x. The other one I do know, minus 2 quantity squared, plus y minus, what's my other y value? 3 quantity squared. And the only thing we're going to do is to unsquare root. So to unsquare root it, we just square both sides. So our answer is going to be 16 equals quantity x minus 2 squared plus quantity y minus 3 squared. So it's really just using the distance formula, and this is the standard form of the equation of our circle. That's all we have to do. So take a look at what we're really looking at. Anytime we have an equation of a circle, we said the center 2, 3 is right here. So we're really just saying, oh, we take the radius, which was 4, and we do what with it? We square it. So the equation of a circle is always going to be r squared equals, and then I'm always going to just have an x, just like I had from before, x minus, where'd they get the 2? From this x value. Now I can't really say x again, so they use a new variable called h. So x minus h squared plus y minus k squared. So that means that r is the radius and h and k is a point that is the center. And that's really all 12.7 is looking at saying, I'm going to look at whatever the radius is and square it, and whatever the center is, I'm going to minus it because that's my distance formula. I'm going to minus the x value of my center and my y value of my center. Okay? So that's really, that's really as simple as it is. So let's come back to that Mike Tyson thing here in just a little bit, because let's make sure we've got that here. So let's say I want an equation of a circle, because it can't be that easy, can it? And let's try it. If I want an equation of a circle, if the center is 3, 6, and the radius is 1. Okay? So all I'm going to do is take my radius and square it. So 1 squared is 1. So 1 equals, then I'm going to say x minus, and I'm going to put in the x value. That's all I have to do. X minus 3 squared. Plus, just like I do with the distance formula, so it's kind of easier again if you understand where it comes from, y minus 6 squared. And that's my answer. Okay? So all I'm doing is putting in the radius and putting in my center for my x comma y center. Okay, let's try another one. What happens if the center is -2, 0 and the radius is 7? Well, still start off with my radius. 7 squared, so I'm going to start off with 49 equals x minus a -2. Now, what happens when I have x minus a -2 squared? You're exactly right. It becomes plus a positive. So you're going to have some of them where it does have a plus sign because my center is negative. So essentially, you're taking the opposite of the sign of the center. If the center was positive, you write minus. If it was minus, you write plus. Okay? What do you do if it's 0? Well, just leave it in. Y minus 0 squared. Do you really have to write minus 0 squared? No. So if you wanted to say 49 equals the quantity x plus 2 squared plus y squared, that's fine also. So what happens if it gets a little trickier and the center is given to me? Well, that's not going to be any trickier because that's just -4, 8. But now it's a little trickier because my radius is the square root of 5. So what am I going to do with the square root of 5? Square it, which is just going to be 5 is equal to x plus 4 squared plus y minus 8 squared. So really not too much different at all, okay? I'm sorry, I got a little shaky there, but I wanted to get it all on one example to show you that really it's going to be pretty simple. So let's go back to Mike Tyson then and say, okay, so now I had that y squared. What would I have if x squared plus y squared equals 34? What would the radius of that circle be? Well, I'm really looking at it as something was squared. So r squared is 34. Oh, so what is the radius of his circle? R equals the square root of 34. You have to square root both sides. Okay? And Mike Tyson had said anybody that could solve that is a rocket scientist. So you're all rocket scientists now. That's all it is. Now, if he asks for the center, it's a little trickier, but that would still be what's being subtracted from the x, what's being subtracted from the y. So if I needed the center, I'm just saying, well, nothing's being subtracted. So you might have the center being 0, 0 as well. Now, one last thing, and that is they're going to ask you to go backwards on that. Okay, so going backwards on that says graph it. Well, all I'm going to do is exactly what we just said. We're going to go backwards. So that means that I have to look at what was being subtracted from my x, what's being subtracted from my y. So my center is going to be 0 because nothing's being subtracted from my x. What's being subtracted from my y? Now remember, that would be like minus a negative to be plus. So it's the opposite sign. So 0, negative 1. Then I know r squared is 9. So what would the radius be? And then you just graph it. So you start at 0, negative 1. Go out 3 in all directions. And make a circle. If you have a compass, that's great. If you don't, then sketch it on your homework. Okay? And what happens then if one's plus and one's minus? You're exactly right. Use the opposite signs. So my center here would be at positive 5, negative 1. What would my radius be? You're exactly right. The square root of 1 is still 1. So I would just go out at 5, 1, 2, 3, 4, 5, 1. Make a dot. Go 1 in every direction. Now, I know those are simple examples to show you, but I want to make sure that you understand that it is that simple. All we're really looking at is r squared equals x minus h squared plus y minus k squared, where the radius is the r, so that's going to be my squared term, and my h and my k are what is being subtracted in here because of my distance formula. Let's look at some more examples looking at your reteach worksheets. And I just wanted to say thank you so much. And these guys were like, yep, that was pretty clever. The square root of 34. Did you know that? No. Well, now you do. Okay? And that I hope you had some fun in learning all this geometry. Don't forget, you can always contact your teacher, and have an amazing summer. Bye.